Here we will see some of the main properties of rotation matrices and what SO3 is. The first property is related to the transpose of a rotation matrix. We can do this multiplication, R transpose times R, and we should recall that R can be represented in terms of X, Y, and Z. So this R transpose will be this same X but transposed, then Y transposed, and Z transposed. The multiplication will give this, for example, X transpose times X, X transpose times Y, X transpose times Z, which is this first row. The second row and the third row can be obtained in a similar way. Here we should remember the following, that every axis here, X hat, Y hat, and Z hat, is a unit vector, and is perpendicular to the other two, because they represent a frame. So because of this, we have some properties. This product between the vector and itself, since it's a unit vector, this will be just 1. This also will be 1, and this will be 1, what you see here. And these terms, these products here, will be 0, because basically they are orthogonal vectors, and the dot product between orthogonal vectors is 0. So at the end you will have this matrix, and you see that this is the identity. You can also do the same thing using R transposed instead of R. So I put here, instead of R, I put R transposed, and instead of R transposed, I put R transposed, again transposed. And I can use the property of the transpose and get this relation. And this is again equal to the identity. You can check this out. Now, why is this important? Because I have the following. R transpose times R equals the identity, and R times R transposed equals also the identity. So if you have a matrix that makes the original matrix be the identity, that new matrix, in this case R transpose, is the inverse. So the conclusion here is that the transpose is equal to the inverse, because as you see here, it gives the identity. So finally, this is true. This is the first property, that the transpose is equal to the inverse. And this means that R is an orthogonal matrix. That's just the denomination of this type of matrices. Now, R is an orthogonal matrix. This means that it has orthogonal rows and also orthogonal columns. For example, here we have column R1, R2, and R3. The property of orthogonal matrices is the following, that if I multiply, for example, this R1 with this R2, the result is 0. If I multiply R1 with R3, the result is 0. And if I multiply R2 with R3, the result is 0. This gives 3 constraints for this first part. Then for the second part, if I multiply each of these with itself, the result is 1. So R1 transpose R1 is equal to 1. The same for R2 and for R3. So again, I have 3 constraints for this. So in total, I have 3 constraints here and 3 constraints here, which give me a total of 6 constraints. Now, it means that the rows and columns form an orthonormal basis in R3. Now, R has 9 elements, but as we have seen, it has 6 constraints due to the orthonormality of the columns. So in total, we have 9 minus 6, 3. So R has only 3 degrees of freedom, or only 3 independent elements. This means that we are using 9 elements, because this is a 3 by 3 matrix, to represent 3 degrees of freedom. So in fact, this is a redundant matrix, because we are using more terms than the needed ones. The second property is related to the determinant of a rotation matrix. We have this from the previous slide, from the property of the transpose. R transpose times R equals identity. We can use the property of the determinant here. We apply the determinant to both sides. Using the property of the product of this, we can solve for this. And then we can use this other property, which is that the determinant of R transpose equals the determinant of R. So we replace this here, and we will have this that squared, and then it would be a root square of 1. So at the end we will have that it is root square of 1 plus minus. So in general, the determinant can be positive or negative. However, we will be using right-handed frames. Right-handed frames follow the right-hand rule, and this means that these relations hold. These cross products will hold. X times Y equals Z, and so forth. So here, this is just to show a little bit what is the meaning of this. I am representing X, Y, and Z, all the components, 1, 2, 3, 1, 2, 3, 1, 2, 3. And if I get, or if I compute the determinant of this, I will get this expression. This is just a normal determinant. Now, using these properties, in particular, using this property, Y times Z, I can express this in terms of each of the components, and I can call this x1, x2, and x3 because of these properties. And then I can replace this back here, and I will get this, that x1 squared plus x2 squared plus x3 squared equals 1. So by using these properties of the right-handed frame, the result is 1. So at the end, the determinant is only plus 1, not minus, only plus. The rotation group is called SO3, and it contains all the matrices that are rotation matrices. And basically, it satisfies these two properties. R transpose equals the identity, and the determinant is plus 1. This is a very important group. It stands for special orthogonal. Orthogonal because we use orthogonal matrices, and special because the determinant is plus 1, it's positive. SO3 represents the rotations of all rigid bodies, and it's a mathematical formalism. Basically, it's a Lie group. What is really important is to know that for a matrix R to be a rotation matrix, it must belong to SO3. In other words, for any matrix R to be a rotation matrix, it must satisfy these two properties. R transpose equal identity, and determinant of R equals plus 1. For example, if we want to determine if these matrices are rotation matrices, we have to apply the previous properties. In the first case, what do? We can first compute the determinant of this matrix. You can do this using MATLAB, Python, Octave, or any program that you want. You don't need to do it by hand. The determinant will be 1/2. So since it is 1/2 and it is not 1, then of course this is not a rotation matrix. Now for part B, we compute the determinant and we get that it is plus 1. We compute this, the matrix R2 times its transpose, and in this case we obtain the identity. So if these two conditions are satisfied, we can conclude that it is a rotation matrix. In this example, we know that this is a rotation matrix. We want first to compute its inverse. We know that the inverse is a transpose because this is a rotation matrix. So we can just compute the transpose, and this will be equal to the inverse. Then B, we want to verify that it is a rotation matrix. We would need to check that these two properties hold, and in fact they do hold. And then we want to compute this transpose, but we have already done it here. You can also verify using a numerical program like MATLAB or Python that the inverse will be equal to the transpose.